Right, this is NCCER Electrical 4, Module 7, Advanced Controls, Module number 26407-20. Advanced Controls. All right, so we're going to talk a lot about different components that are used in controls and stuff like that. If you need a refresher for this stuff, this is all stuff that you have should have talked about in Electrical 3, and then maybe briefly here in Electrical 4. So some stuff I'm going to talk about pretty quickly because you should know what it is and how it works. Some other stuff they go into a little bit more. They talk a lot about, first slide is on solid state relays. They're going to talk a lot about solid state relays. Some of the trade terms that you have that you should know is dashpot, heat sink, solid state overload relay, SSOLR. They're gonna give these abbreviations quite a bit throughout this chapter. So every time I'm not going to say solid state overload relay. You just need to know that's the SSOLR. Solid state relay, they're abbreviating that with SSR. Thermal conductivity and thyristor. You need to know what the thyristor is. Talked about that a couple modules ago. 110 solid state relays. First two sentences are highlighted. The solid state relay, SSR, has many advantages over the electromechanical relay, EMR. It has longer life, higher reliability, higher speed switching, and high resistance to shock and vibration. So there's no moving parts. So this is like the where they say EMR. They mean like an ice cube relay is an example of an EMR where you actually have a coil that pulls in contacts. These solid state relays act a little bit differently, and they can, just like I said, higher reliability, longer life, higher switching speed, and higher resistance to shock and vibration are all advantages of solid state relays. Moving on to page 2. They go through the operation. 111 talks about the solid state relay operation. And then you can have different switching modes. So right before the bullet points it says the switching circuit can operate in one of these 4 switching modes depending on the solid state relay design. If you go to the 4th bullet point on page 2, I have the first sentence highlighted. Analog switching. In this type of relay, the amount of output voltage varies as a function of the input voltage. So in analog switching, the amount of output voltage varies as a function of the input voltage. Page 3, they go through and they talk about the comparison chart for electromechanical relays versus solid state relays. So like the coil voltage and control voltage are comparable in those two. Inrush voltamps or control current. The row that I've highlighted is the second to last one. So where there's no equivalent in EMRs for SSRs, they have the ability to do zero current turnoff. So they can turn off at essentially zero, crossing off the load current that flows through this solid state relay. A thyristor will turn off only when the current falls below the minimum holding current. If an input control is removed when the current is at higher value, turn off will be delayed until the next zero current crossing. So SSRs have the ability to have that zero current turnoff, is what you should know from that. Performance is in table 2 on page 4. I don't think I have highlights or I don't have PowerPoints for that, but you are going to have a question come out of table 2. So one question coming out of table 1, one question coming out of table 2. You need to know the highlight that I have is in response time. When comparing EMRs to SSRs, response time is greater in an SSR, is what you should know from that highlight. 113, 2-wire and 3-wire SSR control. Second and third sentence are highlighted in 113. For 3-wire control, there's no auxiliary contact in an SSR to seal in the relay until the stop push button is activated. So remember, in 2-wire control with a 2-wire control, you're just using a start and then it's turning on the AC load, but there is no ability to latch in your start. So with a 3-wire control, second and third sentence. For 3-wire control, there's no auxiliary contact in SSR to seal in the relay until the stop push button is activated. However, the addition of an SCR and a current limiting resistor will achieve the same results as shown in figure 3B. So down here, I've got an SCR. So this is going to be connected to my start push button along with a current limiting resistor. So when I push start, I'm going to get power flowing through here, and it's going to turn on and it's going to latch, because power will only, once power is flowing through my SCR, it won't stop until I push the stop push button. So this is for 3-wire control. So using 3-wire control, you can add an SCR for your latch. They go through multiple. You can connect to multiple outputs. You can have temperature consideration, over voltage versus over current protection. You can talk about that. We talk more about that with the motor starter and motor contactor section. SSOLR, so solid state overload, solid state protective relay, commonly called a solid state overload relay. First sentence is highlighted. Solid state protective relay, commonly called a solid state overload relay, or SSOLR, protects the motor against damage from overheating. Overloads is mostly are going to protect the motor from overheating. Motor or the wires, the conductors. You're going to have different types of SSOLRs. You're going to have non-programmable SSOLRs. Moving on to page 6. In that first giant paragraph on page 6, probably about 2/3 of the way through, I got a couple sentences highlighted. Right after where you see 1, 2, or 3 loops, I've got the sentence right after that highlighted. The trip point for the SSOLR is set within the range shown on the adjustable trip current dial on the face of the unit, as directed in the manufacturer's instruction. This setting for the SSOLR is based on the motor full load amperage, the service factor, and the number of current transformer loop turns being used. So for non-programmable SSOLR, the setting is based on the FLA, service factor, and the loop turns. I need to note that. Moving on to page 8 and 9, in the programmable SSOLRs, the right-hand side of the page, the sentence that's right before the bullet points is highlighted. The types of functions and trip thresholds that can be programmed with most programmable SSOLRs include the following. I've got the first bullet point, the heading highlighted, overcurrent trip class, with the second sentence. Class 20 is used for most NEMA-rated general purpose motors. That class 20 trip setting is used for most NEMA-rated general purpose motors. And then if you go down to the 7th bullet point, I've got the whole thing highlighted. Undercurrent trip delay. This determines how long the SSOLR will allow an undercurrent condition to exist before it trips. So you have different things that you can program into these programmable SSOLRs. Timing relays 1, 2, 0. You're going to have different types of timing relays. Those are going to be written in the bullet points on page 9. I've got the first 2 bullet points highlighted, 2 separate questions. You got the on-delay relay. An on-delay relay provides a time delay after the relay is energized. And then you've got the off-delay relay. An off-delay relay provides the time delay after the relay is de-energized. So 2 different similar things that are similar but 100% different. Sound similar, but they're different. So you've got the on-delay relay and the off-delay relay. Going on to page 10, you need to know, I've got this symbol on the board. If you can see that, the normally open, timed open contacts, NOTO. You need to know, you should know what all of these are. You should know what the symbol for all of them are. So normally open, timed closed contacts, normally closed, timed open, normally open, timed open contacts, and normally closed, timed closed contacts. So you should know the symbol for all those, but key in on that normally open, timed open contact, or the NOTO. Yep. Solid state timing relays. 121. I don't have anything highlighted in this section, but it is going to be a good section to read through, especially those 2 bullet points on page 11. 122. Timing relay applications. The whole second paragraph is highlighted. You're going to need to know like the order, how stuff is happening. I would recommend reading through this whole section because you're going to see how this circuit acts. But this second paragraph is highlighted. I'll try to as we're reading along, I'll try to point to the different stuff. But if you've done the motor trainer, you should know how to read this schematic. But second paragraph, when start push button is pressed, the circuit is completed from L1 to L2. So circuit's completed from L1 all the way to L2 when start push button is pressed. Through the stop push button, the start push button, the motor starter coil M1 and the closed overload contacts. The energize of the M1 closes its normally open contacts. So M1 closes, closing the M1 contact here, which seals in the start. Seals around the start push button. Simultaneously, the timing relay TR1 receives its power. So TR1 is getting powered by the coil right here and starts its timing delay while motor 1 starts and gets up to speed. When TR1 finishes this time period, the normally open contacts right here will close to energize the motor starter M2 and supply power to TR2. So motor 2 and TR2 after a time delay are started up. While TR2 is timing, motor M2 is getting up to speed. When TR2 finishes its timing period, the normally open contacts close to energize motor starter M3. So M3 is then energized. I do have for this one, you need to know what the timing contacts look like. So that's the TR1, TR2. I have those highlighted on page 13 to go along with that highlight 8. So you need to know when those are working and what they're turning on. I just noticed that I do have a highlight for this picture right here. This is from section 121, the solid state timing relay. You can see this is a plug-in timing relay, and then this would be like the back plane. You need to know, you're going to have a question on which ones are your normally closed contacts. So if I'm looking at this, I can see this is my normally closed contact, so I'm connecting from 1 to 4 is normally closed, and then from 5 to 8 is also normally closed. You'll have that as a module review question. You got section 1 review on page 13. I'm going to continue on to section 2. Section 2, reduce voltage starting method. So this would be reduced voltage, like you're not going to have a spike in voltage to start. but it's going to be, you're going to start these motors with a reduced starting method. You've got two different transitions. You've got a closed circuit and open circuit transition. Won't talk about those too much, but good to read through. You got the conventional methods, 210 for these. In 211, the auto transformer reduced voltage motor starting control. Auto transformer reduced voltage motor starting control. 211. I've got the first 3 sentences highlighted. Auto transformer reduced voltage starters are widely used because of their efficiency and flexibility. All power taken from the line, except for transformer loss, is transmitted to the motor to accelerate the load. Several different taps on the transformer allow for adjustment of starting torque and inrush current to meet job requirements. You want to key in on those starting torque and inrush currents. So the taps on the transformer allow for adjustment of starting torque and inrush currents. The immediate next sentence is a separate highlight. Auto transformer reduced voltage starters are typically used with hard to start loads such as reciprocating compressors, grinding mills, pumps, and similar devices. So that's where they're used. You're going to have this figure 12 on your page 15. You're going to need to look through this. So you've got auto transformers. So remember, an auto transformer is a your primary and secondary coils are one together that are wired in series. So this is like your primary and your secondaries. So you have 3 separate auto transformers that are wired together. And then you just need to follow along as I'm reading through this schematic. My highlight on page 15 in the top right, the first sentence up there in the top right is highlighted. Figure 12 shows a schematic diagram for an induction motor being controlled by a closed circuit transition type auto transformer reduced voltage controller. So if you look at this schematic, you can see my auto transformers right here, and this is I've got figure 12 at the bottom highlighted. This is a typical auto transformer reduced voltage starting circuit. So they go through how this works. The last paragraph on page 15 through the end of that section is highlighted. So I'm going to read through this, but you've got you pretty much need to know how this circuit is going to work. But I'm going to try to read through this slowly while pointing at this stuff as I go. So pressing the start button energizes the timing relay. This causes 2 sets of normally open instantaneous contacts to close. So if I go to TR, I can go and look where my 2 sets of contacts are. So TR will close here, and TR will close here, giving power to the bottom half of this control circuit, and then also sealing around my start push button. One set of closed instantaneous contacts provides holding for the timer. The other set completes an electrical path via the normally closed contacts of contactor R and the timed open contacts TRTO of the timer relay to energize the coil of the contactor 1S. So TR closes, and then I get power to 1S coil right here. 1S will close, which closes in the power side, which closes one side of my auto transformer at the top. When contactor 1S is energized, its power contacts close, connecting the ends of the auto transformers together. So it connects all 3 ends of my auto transformers together. It also causes contactor 1S auxiliary contacts to close. Thereby energizing contactor 2S. So down here at the bottom in the control circuit, 1S closes, 2S is then powered. The normally closed auxiliary contacts of 1S in the control circuit for contactor R open. So R opens up, 2S is closing. This provides an electrical interlock to prevent contactors R and 1S from being energized at the same time. When coil 2S is energized, its power contacts close and connect the motor through the auto transformer taps to the power line, starting the motor at a reduced inrush current and starting torque. The normally open auxiliary contacts of 2S closed to provide a holding circuit for contactor 2S. So 2S closes, so I'll have power to 2S, so these will stay on. And then 1S is also opened up, so my run, so I cannot connect the it's an electrical interlock. Second to last period. You want to key in on this paragraph right here. After a predetermined amount of time, so this is where my timer happens, predetermined amount of time, usually 1.5 to 15 seconds. The timer relay times out and the normally closed timed open NCTO contacts open, causing contactor 1S to de-energize. So my contactor opens up, 1S is de-energized. One side of my auto transformers are no longer connected together. This opens its power contacts and returns it to normally closed auxiliary contacts to the closed position. Simultaneously, the normally open timed close contacts of the timing relay TR close. So the normally TR closed, causing R, the run coil, to energize. Its power contacts close. So contacts close, so it's just going to be, once my R coil comes on, my power from my circuit breaker or fuse just runs straight to the motor. So my 1.5 to 15 seconds of timing just allows my power to run through the auto transformers. Essentially what it's doing. So simultaneously, the normally open time close contacts of the timing relay TR close, causing the contactor R to energize via the closed auxiliary contacts of the contactor 1S. When the contactor R energizes, power contacts close, bypassing the auto transformer and connecting the motor to full line voltage. It's normally closed auxiliary contacts also open, causing contactor 2S to de-energize. So R right here will open up, 2S will de-energize. Note that during the transition from starting to full line voltage, the motor was not disconnected from the circuit, indicating a closed circuit transition method of operation. As long as the motor is running in the full voltage condition, timing relay TR and contactor R remain energized. Only an overload or pressing the stop push button stops the motor and resets the circuit. So pretty much need to read through those 3 paragraphs and see how this circuit operates. Continuing on page 16, 213, why delta reduced voltage motor starting circuit control. I've got the second paragraph highlighted. So you need to know that figure 15, which is a So figure 15, which is what's up on the board, is what it's talking about. So figure 15 shows a schematic diagram for a Y delta controlled by a closed circuit transition Y delta type of reduced voltage controller. As shown, it includes a 3-pole contactor 1S that's used to short motor leads T4 and 5, T4, T5, and T6 during starting to connect the power in the Y connect configuration. A 3-pole contactor 1M energizes the motor leads T1, 2, and 3 for both Y and delta connections. Key in on this, a 3-pole contactor 2M. So you see your 2M contactor up here at the top, 3-pole contactor. Coil is down here, contactor is right here, 3 poles. Energizes motor leads T4 through 6. So coming through here, 4, 5, and 6. During the running to connect the motor in a delta configuration. So contactor 2M connects this to run in a delta configuration. As you have it also includes a 3-pole contactor 2S that connects resistors in series with motor windings during the start to run period. Note the contactor 2S and the resistor bank are unique to the closed circuit transition starter. An open circuit transition starter does not have these components. All right. So you should be able to read through your schematics by now, especially after Electrical 3. So just reading through schematics, very basic for this book. Moving on to page 17, 220, solid state reduced voltage motor starting control. First two sentences of 220 are highlighted. Solid state reduced voltage starters perform the same function as electromechanical reduced voltage starters, but they provide a smoother stepless start and acceleration. For this reason, they are often referred to as soft start controllers. These are referred to as soft start controllers, what you want to key in on in 220. Soft start controllers is what it has up here on the board. Page 18, you've got your figure 15, which is what I just talked about. And then your simplified solid state reduced voltage starting circuits you can see on figure 17. But I'm going to go on to page 20. So still in 220. The first bullet points on page 20, the sentence before them is highlighted. Some starting characteristics that normally can be programmed include, so this is programming into the SCR. So I've got the first sentence of ramp start highlighted. Ramp start, shown in figure 19A, is the most common form of a soft start. 19A, you got your locked rotor torque, you got your ramp start, so you have you ramp up your amperage, and then it'll drop down for your full load amp. Most common, this is usually how motor starts up. Next bullet point, the kick start. So this is figure B, first sentence of that's highlighted. Kick start, shown in figure 19B, provides initial boost of current to the motor to help break free the motor and start the motor. So you're going to have a spike in amperage to help get this motor going. So where you have large amount of locked rotor torque, you're going to use this kick start. That's all I've got for section 2. You've got 2 questions on page 23. I'm going to continue going with adjustable frequency drives, section 3. All right, section 3, adjustable frequency drives. They will call adjustable frequency drives AFDs. You might also hear them called VFDs, variable frequency drives. Usually more commonly known as variable frequency drives. But trade terms to know. Carrier frequency is going to be a good one to know. You just need to know that these can have a lot higher frequencies than regular drives and stuff like that. You also need to know slip. You should know what slip is. Slip is like from electrical 1. But the IGBTs, that second to last trade term, the insulated gate bipolar transistors. Everybody this is just called IGBTs. We're going to talk about them throughout this chapter. Like they're integral into how VFDs or AFDs work. This is a type of transistor that has low losses and low gate drive requirements. This allows it to be operated at higher switching frequencies. So you can open them up insanely fast with not a lot of loss. So if you look just very, very, very basic on how a adjustable frequency drive works. Actually, let me give you my highlights and then I'll talk about it. Nothing highlighted on page 24. Going on to page 25, AFD forms and types. First thing highlighted in 311. The National Electrical Manufacturers Association, or NEMA, describes 3 AFD drive classifications according to the relationship between their input and output. So whatever you have coming in versus whatever you have going out, they have different types. I think there are several different types, but they key in on these 3. And then I highlighted the third one, the form FC. So the AC input to DC intermediate bus to AC output. These are the most common and will be the focus of this module. So AC in, DC in the middle, and then AC out. Essentially how it works. Kind of. Components of an adjustable frequency drive. AFD has 4 main sections. You should know what all those sections are. If you want to get into variable or adjustable frequency drives, you need to know these different sections. I've got the second section highlighted, DC bus. The DC bus includes capacitors and inductors, or LC filters, which create LC circuits, as necessary to smooth the DC voltage and provide robust power near the peak voltage of the incoming AC waveform. So, out to the side of that, I wrote LC circuit, which is the LC filters. You also have you also use bridge rectifiers to create smooth the DC voltage. You're using these to smooth out the DC voltage. Let's see what else. Also coming from, this is coming from 311, up at the top of page 25, like table 5 compares the key features of each type. So if you flip over, you've got 6 different types of control methods in table 5, which I missed this one in the first section. So you did have 6 different types of control methods. What they're wanting what I have highlighted is the speed range at constant torque. So your speed can change, but you're going to have constant torque throughout. You're going to use from all the way to 0 to 100%. You're going to use the feedback vector. So vectors are what you're going to use in this, but the feedback vector is what you're going to use for constant torque throughout a 0 to 100 speed range. So just looking through this figure 20 on the board, but it's essentially what you have is AC coming in. You create DC with the diode bridge rectifier, like you create DC power, and then you have all kinds of control that's gonna take DC, and you're gonna switch the power on and off to create a fake AC sine wave with DC. So the output is an AC waveform, but it is created with DC by that IGBT inverter. So remember that IGBT has transistors in there that switch on and off and can create this waveform, and you can smooth it out over time. So your voltage is on or off, but your current, this happens so fast, you create an AC waveform with DC. 320, page 27. I keep wanting to say variable frequency drive, adjustable frequency drive uses and benefits. So you're going to have a lot of these are going to be, rather than having on-off control for certain things, you can have a varying or an analog control for different motors and stuff like that. I would read through all of these bullet points, and then just note a lot of it's going to have to do with different, obviously if you have a AFD, you're going to want different speeds, so different speeds for different functionalities and stuff like that. You're going to have energy savings because you don't have to have Maybe you don't have to have the blower motor on 100%. You can turn it down to 70% or something like that, to where you're going to gain some of that energy savings back. You do want to read. I would read through that energy savings bullet point, because that is going to be one of the biggest energy savings in advanced control is why you're using AFDs. AFD selections, a bunch of different types of adjustable frequency drives. We've got the Allen Bradleys in the lab that you guys will or have been working with, but they got different bullet points for different functionalities. I've got the heading of the second bullet point up in the top right of page 27 highlighted. Constant torque loads, along with the second to last sentence in that bullet point. With these loads, the torque remains constant over the speed range, but horsepower increases as the speed increases. And then I also have the next bullet point, first sentence highlighted. Constant horsepower loads. With these loads, as the speed increases, the torque decreases, so that horsepower stays the same. So depending on what you want, you can have the different types of loads. Not depending on what you want, but those are the different types of loads for determining what adjustable frequency drive you will use. You're also going to be looking at, moving on to page 28, you need to look at that operating frequency range, which is figure 24. This picture right here. You're gonna have several questions come off of this picture right here. I've got the first 2 or 3 sentences highlighted. Motors operate over a wide frequency range with minimal heat losses when the ratio of input voltage to frequency matches the ratio of the nameplate voltage to frequency. So as long as that ratio is right, you'll be okay. This is a range with a constant volts to hertz ratio, as shown in figure 24, it provides constant torque from the motor. So from point frequency minimum to point FB, which is the base frequency, you have a constant volts to hertz ratio. I want you to circle that and highlight that, whatever you need to do. But from the frequency minimum to the base frequency, you have a constant ratio of volts to hertz. And then once you reach the base frequency, from the base frequency to the maximum frequency, you have constant voltage. Highlight that. So you want this section here highlighted for constant volts to hertz ratio, and then this section right here, you have constant voltage. Your output voltage doesn't change from your base frequency to your maximum frequency. So those 2 sections you want to mark on this picture. I have a couple of questions come out of there. Going along with that section, the last bullet point, which is on page 29, is highlighted. Matching the adjustable frequency drive to the motor design is important. As shown in table 6, NEMA design A, B, and E motors are best suited for use with an adjustable frequency drive, although an adjustable frequency drive can be used with other motor designs. Those 3 are the most common though, A, B, and E. They go through programming. I don't have anything highlighting programming, but you will program a VFD in the lab. 323, AFD application precautions. First bullet point's highlighted. Any fan-cooled motor is at risk of overheating and failure when the AFD operates at slower speeds, 50% of its base speed or less, for more than a few minutes. To prevent this, an externally powered fan must be used to maintain the needed cooling airflow. This is particularly true if the motor has a Class F temperature rise or a 1.0 service factor. So, if you want to slow your motor down, that's fine. But remember, like that usually in a motor, your fan is connected to the opposite drive end. So if it slows down, you're not going to get as much cooling on the motor. So if that's an issue, you have to connect an externally powered fan to this motor so you get the correct amount of cooling. The last bullet point on page 30 is also highlighted. A motor powered by an AFD often has parasitic or stray voltages coupled to the motor shaft. If these voltages are discharged through the bearings, that cause an electric discharge machining of the bearing races, typically in the form of parallel grooves called fluting, and premature bearing failure. Key in on this next sentence. Certain types of AFD output filtering or the use of a shaft grounding bushes will prevent this problem. Other methods sometimes available include the use of electrically insulated bearings or shaft couplings. Key in on that second to last sentence. So you've got 2 questions for section 3 review on page 34, and I'm going to continue on for section 4, motor braking methods. You've got different types of motor braking. So you're going to have DC injection braking, dynamic braking, or regenerative braking, and then friction braking. All these are going to be different but the same. They're all going to brake the engine, introduce some form of braking into the engine. 410 DC injection braking. First sentence is highlighted. DC injection braking utilizes a DC voltage applied to or injected into the motor stator windings for a timed interval. So this is another one where you should we do in DC injection braking in the lab. If you didn't do that in electrical 3, you will do it in 4. Skip a few sentences, and like the second to last sentence in the bottom left of 35 is highlighted. An advantage of DC injection braking is that motors can be stopped rapidly without wear on brake linings or drums. So where you have friction braking, you've got drums, it's like a car drum brake that stops the motor. With DC injection braking, there's none of that. So there's no like physical wear that's happening. On the right-hand side of the page, you're going to have, he's going to talk about this DC injection braking circuit. This is figure 27, which should be on page 36. So you can go through the schematic and see how your DC injection braking is working. I do have the second bullet point on the right hand side of page 35 highlighted. Simultaneously, timing relay TR. So your timing relay TR right here is de-energized, closing its normally open, timed open, normally open, timed open contacts. The next paragraph, first 2 sentences are highlighted. Got a couple questions coming out of those first 2 sentences. A transformer with tapped windings is often used to adjust the amount of braking voltage applied to the motor. Current limiting resistors could be used for the same purpose. Current limiting resistors could be used for the same purpose. So you need to, I would read through that page 35 and read through how this bridge rectifier is turned on so that you inject DC voltage directly into the stator of the motor to stop it. Page 36, dynamic and regenerative braking. 421, dynamic braking. I've got the heading underlined, dynamic braking. Along with the whole first paragraph, you're going to have a couple questions come out of the first paragraph. First sentence, key in on the first sentence. In addition to the use of an adjustable frequency drive for DC injection braking, the AFD can also provide dynamic braking by the use of timed or ramped stop for motor and its driven load. When the output frequency from the drive to the motor is less than the speed of the motor, negative torque is developed within the motor. This motor then acts like a generator by converting mechanical power from the shaft into electrical power that is returned to the DC bus within the adjustable frequency drive. Key in on the rest of this paragraph. Adjustable frequency drives are made with an IGBT switch connected to its terminals, which in this application are connected to external braking resistor, where the excess energy gets dissipated as heat. So your energy is essentially put through a resistor and is dissipated as heat. Regenerative braking. Regenerative braking is what a lot of hybrids, like cars, like Teslas and Priuses and stuff like that use. When you let off the gas, you will feel your car slow down. That's because your wheels, your motion is being turned into regenerative energy by slowing down your car. I have the first bullet point, 422 highlighted. Regeneration to the power line. AFDs that can do this are called line regenerative. They are made with active components in their input section instead of diodes. When the DC bus voltage reaches its upper safety limit, the AFD's logic returns the excess energy back to the incoming power line. So they regenerate this energy. 430, friction braking. First sentence is highlighted. Motor braking is also done using solenoid-operated friction braking. So this solenoid is often operated by whatever's controlling these contacts for your line, or these motor starters. So whenever this is off, this is on, which stops your motor. Next paragraph, first two sentences are highlighted. Many friction brakes used with motors are like those used with vehicles. They normally consist of two shoe or pad type friction surfaces that contact a wheel mounted on the motor shaft. You have to use this friction braking stuff with like cranes and stuff like that, because if you use like dynamic braking, if you lost power, a crane cannot hold a load with no power using dynamic braking, so you have to use this friction braking where there's a physical device that is holding the load. That is all my highlights for section 4. I'm going to continue on to section 5, working with motor controls. Section 5, no trade terms in section 5. 510, precautions for working with solid state controls. First bullet point that's on the page, I've got the third sentence through the end of the paragraph, or almost through the end of the bullet point highlighted. Always ground yourself before touching a board, like any kind of circuit board or anything like that. Disposable grounding wrist straps are sometimes supplied with boards containing electrostatic sensitive components. If a wrist strap is not supplied with the equipment, a wrist strap grounding system should be obtained and used. It allows you to handle static sensitive components without the fear of electrostatic discharge. So everybody knows you can go touch a door handle, especially in the winter and get some like a static shock. We all can have a buildup of electrons in our body that will be released into ground if we are grounded. If we release this into a circuit board and are grounded through a circuit board, this can cause major issues inside that circuit board. So we can have a grounding strap around our wrist that's connected to ground, to where essentially grounding our body to touch these sensitive pieces of equipment. This is done with like big time with anybody that repairs cell phones and stuff like that. You should have some type of grounding wrist strap, or if you're building a computer or something like that, good idea to have these grounding wrist straps on. Right after the first set of bullet points, I got that whole paragraph in between sets of bullet points on page 40 on the right hand side is highlighted. Electrical noise can also affect the operation of solid state controls. Sources of electrical noise include machines with large, fast changing voltages or currents. When they're energized or de-energized, such as motor starters, welding equipment, or adjustable frequency drives, and other inductive devices, following are basic steps to help minimize the electrical noise. I've got the second bullet point on page 41 highlighted. Using shielded wire to reduce the magnitude of the noise coupled into the low-level circuit by electrostatic or magnetic coupling. Using shielded wire, been in instrumentation. If you haven't, you can have like a shielded wire has like an aluminum foil covering on either the individual twisted pairs or the overall jacket or both. But this can reduce noise or electrical noise. 520 motor control maintenance. If you're cleaning these different things, you can have a conductive tote box where you're not. A lot of times these big drives have circuit boards that you have to input. Like it's not just a big drive. Like some of these big drives have cabinets of controls where you have to change out the circuit boards and stuff like that. But for these, last paragraph on page 41, first sentence is highlighted. Clean the parts of a control equipment by vacuuming or wiping with a dry cloth or soft brush. So you don't want to have a lot of action going on in these circuit boards and stuff like that, but you're using a vacuum, a dry cloth, or a brush. You're not using compressed air. A lot of people use compressed air for these. They are not recommending use compressed air. I used hand air whenever I was doing this stuff. But might be a bad idea. We did have computers go down. Never had a drive go down, but definitely had computers go down from using canned air. Page 42, I've got 3 more test highlights on page 42. And they're all in the second, pretty much the second paragraph. The first one is the third sentence. When the contacts, this is talking about for like contacts for motor starters and stuff. I don't have a picture, but third sentence. When contacts are new, they are smooth and have uniform silver color. Next one. So next sentence. As the device is used, the contacts become pitted and the color may change to blue, brown, or black. These colors result from the normal formation of metal oxide on the contact surfaces and are not detrimental to contact life and performance. Next highlight. Contacts should be replaced in the following conditions. First bullet points highlighted: insufficient contact material with less than a 64th of an inch remains. Replace the contacts. I have never replaced contacts due to low surface. It's usually due to pitting, stuff like that. Like it never gets down to the point where the surfaces are so small. Usually it's irregular surface where pitting. You got 2 questions for the section review on page 43. I'm going to continue on to our last section, section 6, motor control troubleshooting. Motor control troubleshooting. You're going to have basic troubleshooting practices. You're going to have a bunch of different sections in this, like customer interface, physical examination, basic system analysis, manufacturer resources. So there's a lot of resources by Allen Bradley or Siemens or GE. A lot of these put out resources that you can read. They also offer classes. Pretty expensive, but if you can get your job to pay for it, there are good classes to be able to go to. Nothing on page 44 is highlighted. Page 45, 615, troubleshooting motor control circuits and components. The second paragraph, which is at the top right of page 45, is highlighted. The power circuits represented by the heavier lines shown in figure 32, which is figure 32, which is up here on the board. The heavier lines are the power. Figure 32 provide line power to the motor. Line voltages are usually 240 volts or 480. As shown, the power circuit include the disconnecting means, which is the contactor, the overcurrent protective device, fuses or circuit breakers, thermal overloads, fuses or circuit breakers, a normally open contactor contact. Okay, so I messed up. Contactors line voltage are usually, as shown, the power circuits include the disconnecting means. That's your switch up here, then your fuses, then your contactor, normally open contactor, the motor overload device, which is down here, which is your thermal overload heating elements, and then the load circuit. The load is your AC motor. So the load for this circuit is the motor itself. That's the main thing you want to key in on, is the load is the AC motor. Last line of that paragraph. Skipped a paragraph, and in the second to last paragraph on page 45, the last sentence is highlighted. The same basic procedure used to troubleshoot a motor starter works for contacts, because the motor starter is a contact with added overload protection. Contactor is the same as like out in the lab, you've learned that by now. Contactor is a motor starter is just a contactor with overloads built in underneath it. Pages 46 and 47, you can have a fault troubleshooting table for motors and contactors, but they go through the steps on how to go through and troubleshoot. I don't have any of these highlighted, but I would advise reading through them. 620, universal troubleshooting procedures, that continue on page 48-49. In table 7A, 7A and 7B on 48-49, I'm just going to let you know you've got two practice test questions that come out of this. I'm not going to give you what they are, but you're going to have two practice test questions that come out of 7A and 7B. Tables on 48-49. 621, input voltage or voltage imbalance measurements. So you're going to need, you have to have balanced voltage and current for the most part for these different loads, and you'll have to measure that. Third paragraph in 621, first three sentences are highlighted. Voltage imbalance is very important when working with three-phase equipment. A small imbalance in phase-to-phase voltage can result in a much greater current imbalance. With a current imbalance, more heat is generated in the motor windings. Key in on that last sentence. With a current imbalance, more heat is generated in the motor windings. Skip a sentence, and the sentence after that is highlighted. For this reason, the imbalance between any two legs of the voltage applied to a three-phase motor or system should not exceed 2%. So the voltage imbalance between the two should not be 2%. Next paragraph, last sentence on the page, is also highlighted. Current imbalance in any one leg of a three-phase system should not exceed 10%. So voltage imbalance between phases, 2%. Current imbalance in one leg of a three-phase system should not exceed 10%. They go through on how to check fuses and circuit breakers. You did this day one of the electrical motor trainer. I'm not going to go through this too much. Nothing highlighted in 622. Fuse checks, circuit breaker checks. First sentence on page 51 is highlighted. The measured line and load voltages should be the same if the breaker contacts are closed. So you're just making sure that a circuit breaker is working by seeing if the voltages on both sides are the same. If they're the same, then it's closed and working. Pages 52 and 53. Nothing highlighted on those. They go through. 52 goes through like checking your voltages and current coming off of your circuit breakers or your fuses. 624, troubleshooting control circuits. Control transformer checks. Nothing highlighted in those. Read through those. Page 54, contactor relay coil resistance checks. So if you're checking the resistance of your coils. On page 55, that paragraph that's continued over from 54, I've got, if you look directly to the right of the troubleshooting safety on page 54, where it says figure 38, I've got that sentence highlighted. As shown in figure 38, a reading of 0 ohms indicates a shorted coil, and a reading of infinite resistance indicates an open coil. So, that if you have a coil, will show a connection, but usually these coils have like 117 ohms, something like that. I know that's the contactors that's on ours. On our stuff has this 117 ohm resistance, but if it is a dead short, that means that the wire of the coil has been contacted together, and my coil is a shorted coil. That is all my highlights for this chapter. You've got the section 6 review on page 57, the module review on page 58 and 59 and 60, supplemental exercise on page 61, and the practice test for this chapter.